everyone. Welcome to Next Lab, Lab Unit 3. So, in this lab, this video will probably be pretty short. Hopefully you have read the lab handout before watching this video. This lab is all about heat treatment of steels or metals, but we are using a specific steel, these steel bars. This is a 4140 steel. The first four in the 4140 lets you know that molybdenum is one of the primary extra alloying elements, along with our iron and carbon. The 1 in 4140 lets you know that chromium is a portion of the alloying composition, and 40 at the end means the same thing, 0.4% carbon. So this is a hypoeutectoid steel. It is to the left of the eutectoid composition of 0.76 weight percent carbon. And what that means is as we cool and cross the eutectoid point, we're going to have some extra what we call primary ferrite that forms before we get our pearlite microstructure beneath the eutectoid. And what this lab is all about is we're looking at TTT diagrams, which don't just take us to the phase diagram, they actually take us on a third axis away from the phase diagram, which is time. So we see the influence of cooling rate on the microstructure, because depending on how we cool this 4140 steel from the austenitic temperature, around 800 Celsius, we can get a variety of microstructures, each with their own fun, unique properties. We can get pearlite, which comes in coarse pearlite with thick layers of ferrite and cementite. We can get fine pearlite with thin layers. We can have bainite, which has upper bainite and lower bainite, depending on the temperature. The microstructure changes a little bit. We can have martensite if we cool it extremely rapidly. If we quench it, we get martensite, which is extremely hard and brittle, and also a different crystal structure, body-centered tetragonal. And finally, which we're not doing in this lab, but you can do if you take any of the phases, perlite, bainite, martensite, austenite, you heat it just beneath the eutectoid transition temperature, and you hold it for around a day, 24 hours, you get what is known as spherodite, which is very soft, very ductile, much closer to pure ferrite than any of these other phases. So what we're going to do in this lab, it's kind of three parts. The first part is the actual heat treatment itself. We're producing 4 samples. The second part is we are going to do tension and hardness tests on each of the 4 samples that we've heat treated. And the third part is we are going to do polishing, etching, and examining of the microstructures. So for this, I'm going to show you one of the 4 heat treatments. For these samples, we're going to take all 4 samples start at 850 Celsius, that is above the austenitic transformation temperature. One sample we're going to take from 850, we're going to quench it directly in oil, hopefully obtaining a martensitic microstructure. The second we're going to quench in oil, and then we're going to actually put it back in a 700 degree C furnace for an hour. That will hopefully give us a tempered martensite. The third sample we're going to take from 850 furnace, we're going to put it in a 700 degree furnace for 2 hours. Ideally that is a coarse pearlite type. And the fourth sample we're going to take from the 850 furnace, and we're going to put it in the 620 C furnace for 1.5 hours. And that will ideally be a more finer pearlite microstructure. So I'm going to show you how to quench a sample. Quenching is kind of the big new shiny thing in this lab. The other 3 just involve taking it from one box and moving it to another box. And after I do the quenching, I'm going to go perform the hardness test and tension test myself. You have seen these tests performed. It's the same. We're going to do Rockwell B, and we're going to do steel tensile hardness the same as in the first lab, so I'm not going to repeat that. And then we're going to do I'm going to do the polishing and etching process for all of them. Again, it's the same process as with lab 1.3, where we sectioned our 1018, 1045 steel samples. We polished, etched them, and then I'm going to show you the microstructures for these samples. So we're going to go from here. I'm going to show you a quench, and then we're going to go way far in the future, and I'll show you the microstructures after all the testing is done, and I'll upload the hardness, tensile data, and the microstructure images. So let's go look at the furnaces, and then let's quench a sample. All right, these furnaces are, as I mentioned, at various temperatures. We have our starting furnace for all of them, 850 Celsius. We have a furnace over here, which is our 620 for 1.5 hours. And then all the way over here, that's a broken one. We have our 700 furnace for 2 hours. And behind these in the back, on the back wall, we have our furnace where we quench our sample, this one in oil, and then we put it in a 700 furnace for 1 hour. So what does 850 Celsius look like? Let me show you. There's a little window on the inside, lets you know it's a little orange, but if we open the furnace, you can see 850 Celsius, very orange, very warm. You see I have a few of our tinsel bars in there already. We want them to reach their austenitic temperature, so they need to sit in there for at least 12 hours to equally be 850. And if we want to check, just opening that door, it dropped from 850 to 830, but this is a pretty good furnace, so it is going to reheat back up relatively quickly. So I am going to set the camera down, and I'm going to quench a sample. All right, so to be moving this 850 degrees C tensile bars, it is important that we take proper safety precautions. I have my nice smock, which basically covers me from my chest all the way down to my feet in case I drop the bar, it doesn't touch my clothes and burn. It is 850 Celsius, it will burn straight through everything. I have safety glasses in case there's any sort of sparks or anything to protect my eyes. I have some very well insulated gloves, and in order to actually grab the bar itself, I have these nice metal tongs. So I'm going to quench it in an oil bath, which is this guy right here. This is known as quenching oil. It's a little bit different than your car oil. Not quite the same, but it has, roughly the same consistency. So the key for quenching is to be deliberate with your things. We're going to take our bar out of the furnace. We're going to take it out, we're going to close the door, and we're going to very quickly bring it over here and dunk it in the bath, completely submerge it, and let it sit until it cools down. You don't want to be, gentle or, very slow with it. Ideally, you don't want to splash, but you want to be quick and you want to be deliberate. That way, you're predictable, you're safe, and you don't allow the microstructure to change much by cooling in the air. You can get a very rapid cool in the oil. So, I'm going to go grab this thing, and let's do it. Real quick, here's our bar. You see it is red hot, very, very hot, into the oil. There's not much to see, but if you look, you can maybe see a little bit of bubbles along our surface. Where our bar is cooling. By quenching, hopefully we can pass the nose of our TTT diagram and avoid the formation of any sort of pearlite in our microstructure. Now, in reality, there's probably going to be a little bit of pearlite just because I believe the time at the lowest time for pearlite formation is around 3 seconds. So you don't have a lot of time to immediately cool it. But hopefully it's mostly martensite. So this is going to sit here for about a minute. I'll let it cool all the way down, and then I'll take it out and I'll show you what it looks like. So after taking our sample, quenching it in the oil, taking it out, I've rinsed it off. This is our original sample. You see nice, shiny, silver, and after rinsing it, all the oil off and cleaning it, we get this sample. Quite a bit corroded because it was so hot. It got a nice oxide layer on top of it. This oxide, while it's kind of weakly bonded to the surface, it is brittle and hard, which means when we were going to perform our Rockwell B tests on our sample, we want to make sure we're indenting the metal and not the oxide. So to fix that, we have this abrasive steel wire brush to my left, and I'm just going to use that to remove the oxide layer on this medium section here where I will be taking the hardness tests on the sample. So let's move the camera and go do that. Here's our wire brush. It has this basically steel wool little spinning wheel. It spins, and it's very abrasive, and we're going to use it to remove the oxide on this middle section here. So it just, once you turn it on, it just requires a little bit of pressure and rotation, and as always, it's critical to watch your fingers and wear eye protection. So let's do this. And just like that, I have taken this oxide and turned it into this. So you can hopefully see we are seeing our nice steel beneath our oxide layer. So that is heat treatments. Not too bad. The good news is that the difficulty of heat treating metals often just comes from the weighting aspect. So our quench directly into oil is nice because we can do that and we're done in 10 minutes. But our other samples, we need to quench in oil, then put in 700 C for an hour. We're waiting an hour and a half for 620 and 2 hours for 700. But once those are complete, we can use our abrasive brush, which I just used, to remove the oxide layer on our samples. You want to make sure that you remove the oxide but don't hold it for too long, because it does involve friction, which can heat up your sample and then affect the microstructure. So just a little bit is needed. And now that I have this one complete, I'm going to complete the others in the set and go perform hardness tests, go perform tension tests, and then I'm going to section these, mount them, polish them, and I will meet you back at the microscope to look at the microstructures. Thank you. So we're at the microscope. I have polished and etched all of our samples, and now we're going to go through each one of them just to give you a reference for what the microstructures look like. And we will start with, we can start with a 700 Celsius sample that we held for 2 hours. So we would expect this sample to be some form of perlite. And 700 Celsius, it's a little bit higher on the TTT diagram. So this is likely to be our coarse perlite. And as you look, you can hopefully see we have some definite perlite layers, layered structure, ferrite and cementite, especially right here. Let's go ahead and put that scale bar on. Right now we're at 50 times. So you see at the bottom we have a 20 micron scale bar, and we have some nice, really well-defined layers of cementite and ferrite in our coarse perlite sample. And if we slide around a little bit, see we have regions of kind of more dense perlite, but we definitely have quite a few spots of open layers where you can clearly see the cementite and the ferrite. Okay, so now let's look at our 620 for 1.5 hours. Okay, so this is lower temperature, so we expect this to be more fine pearlite structure. And if we zoom in, you can hopefully see we have definitely less well-defined layers like we had in our coarse pearlite. If we zoom in, at 100 times magnification, which is what we're at right now, you can hopefully see we have some very thin layers, kind of, especially in this middle sample here, of ferrite and cementite. We still have the nice grain structure with clear proeutectoid ferrite, which is the kind of the light regions, because we are a hypoeutectoid steel. And we have our fine pearlite around. So definitely pearlite, definitely dark regions, but we don't see the big layers that we saw with our 700 Celsius sample. Okay, so we're gonna go to our fourth sample, which is our quenched. So we took it from 850 and we put it directly into oil. So let's go to 20 times magnification. Get it in focus. And we see quite a big shift in the microstructure. Let's go to 50. So you see this is our martensite structure, and you can hopefully see we have these kind of very sharp needles that are sort of randomly oriented in the microstructure. And these needles are very brittle, and because they're kind of randomly oriented, they are brittle overall, which gives martensite its extreme hardness, but also its very, very low ductility. And the scale bar is correct, so you see these needles are on the order of, I don't know, around 10 microns long and 3 to 4 microns wide, maybe a little bit thinner, but it's pretty consistent. We have this sort of needle-like structure. And remember that martensite has a body-centered tetragonal crystal structure, so a little bit different. Almost too brittle to be useful. So we go to our fourth sample, where we have taken our quenched martensite sample and then we have heated it at 700 Celsius for 1 hour to ideally, hopefully, get tempered martensite. Which is kind of difficult to visualize, but hopefully you can see we still have our needles. Let's zoom in to 100 times. So we still have traces of our kind of needle structure. You can see it here, kind of here as well, but we start forming a kind of more uniform, you see they look like tiny little particles, kind of more uniform structure with less irregular needle shapes. And if we move around, so our very, very long needle structures, kind of, because we heat them up back up to around 700 Celsius, they start to kind of normalize and become less elongated. And ideally, this This does decrease our strength and hardness, but it has a huge increase on the ductility of our sample, which you have seen by looking at our tensile data and our hardness data. So, and let me fix the scale bar. So 10 micron scale bar, so you see these features are pretty small, and this tempered martensite is, the features are pretty tiny, which is why we needed to polish it and etch it to such a high degree. Okay, let's go back to me. That was the steel heat treatment lab. So we took our 4 4140 tensile bars, we heat treated them to ideally get martensite. We got tempered martensite by heating our martensite at 700 Celsius for an hour. We also produced a coarse perlite sample by heat treating at 700 for 2 hours, going from 850 to 700. And we got a more fine perlite structure by going from 850 to 620 for 1.5 hours. And if you follow on the 4140 TTT diagram in the handout, the goal is to see that the microstructures that you observe match what we expect in the TTT diagram. So that is the lab, and that is heat treatment of steels. We have learned that composition matters, temperature matters, but also time matters, which is a thing that the phase diagrams just do not tell us, and we need these extra TTT diagrams to reveal in our samples. And these TTT diagrams exist for a wide variety of steels and other materials, but they all are, each one is only made for a single composition, so they are very, very specific to the material itself. So that is the lab, and in the next lab we will be heat treating brass, which has a little bit different microstructure, and we can learn some new features, new effects of temperature on the grain shape, grain size, and the properties. Thank you.